JEE 2025 Advanced Paper 1 Simple harmonic motion meets rolling motion. A disc rolling inside a ring attached to a spring. Most students panic seeing this setup. But there is a beautiful energy method that cracks it in under 3 minutes. Let me show you. First, let us understand the setup. A fixed ring of radius capital R. Inside it, a disk of radius small r and mass m rolls without slipping. A spring of constant K connects the disk center to the ring periphery along the arc. At equilibrium, the disk sits at the bottom. We need omega for small oscillations. The key observation. This problem has two restoring mechanisms. Gravity pulls the disk back to the bottom when it moves along the arc, and the spring also pulls it back. Both contribute to the restoring force. And because the disk rolls without slipping, we need to account for rotational kinetic energy. The smartest approach? Use the energy method. Let theta be the small angular displacement of the disk center measured from the center of the ring. The arc displacement of the center of mass from equilibrium is x equals open bracket capital R minus small r close bracket times theta. This is the distance the disk center has moved along the circular path of radius r minus r. Now let us write the potential energy. Gravity. The disk center has risen by a height h. For small theta, h equals open bracket r minus r close bracket times open bracket 1 minus cosine theta close bracket, which approximates to open bracket r minus r close bracket times theta squared over 2. So gravitational PE is mg times open bracket r minus r close bracket times theta squared over 2. Spring potential energy. The spring stretches or compresses by the arc length x equals open bracket r minus r close bracket theta. So the spring PE is 1/2 kx squared, which is 1/2 k times open bracket r minus r close bracket squared times theta squared. Both potential energies are proportional to theta squared. Classic SHM signature. Now the kinetic energy. This is where most students make the mistake. The disk is rolling without slipping, so it has both translational and rotational kinetic energy. Translational KE is 1/2 mv squared, where v is x dot, the velocity of the center of mass. Rotational KE is 1/2 I omega rotation squared. For a solid disk, moment of inertia I equals 1/2 mr squared. And the rolling without slipping condition gives us omega rotation equals v over r. So rotational KE becomes 1/2 times 1/2 mr squared times v squared over r squared. That simplifies to 1/4 mv squared. Total KE equals 1/2 mv squared plus 1/4 mv squared equals 3/4 mv squared. Now substitute v equals x dot equals open bracket r minus r close bracket times theta dot. Total KE becomes 3/4 m times open bracket r minus r close bracket squared times theta dot squared.
The effective mass for this system is 3/2 m. This is because rolling adds 50% more inertia compared to pure sliding. Write the total energy. E equals 3/4 m times open bracket r minus r close bracket squared theta dot squared plus 1/2 mg times open bracket r minus r close bracket theta squared plus 1/2 k times open bracket r minus r close bracket squared theta squared. Since energy is conserved, dE by dt equals 0.
Differentiate with respect to time. We get 3/2 m times open bracket r minus r close bracket squared times theta dot times theta double dot plus mg times open bracket r minus r close bracket times theta dot times theta plus k times open bracket r minus r close bracket squared times theta dot times theta all equals 0. Cancel theta dot from every term since the disk is moving. After canceling, we get 3/2 m times open bracket r minus r close bracket squared times theta double dot plus mg times open bracket r minus r close bracket times theta plus k times open bracket r minus r close bracket squared times theta equals 0. Divide everything by open bracket r minus r close bracket. Rearrange to get theta double dot equals minus something times theta. We get theta double dot equals minus 2 over 3 times open bracket g over open bracket r minus r close bracket plus k over m close bracket times theta. Comparing with the standard SHM equation, theta double dot equals minus omega squared theta, we read off omega squared equals 2/3 times open bracket g over r minus r plus k over m close bracket. Therefore, omega equals the square root of 2/3 times open bracket g over r minus r plus k over m close bracket. That matches option A perfectly. Let us do a quick sanity check. If k equals 0, no spring, omega reduces to root of 2g over 3 times r minus r. That is the known result for a disk rolling inside a ring under gravity alone. It checks out. The takeaway: whenever you see rolling plus SHM, use the energy method. Write total energy as KE plus PE. Differentiate and compare with standard SHM form. Remember, for a rolling disk, effective mass is 3/2 m. That 2/3 factor shows up because of rolling inertia. Most students get this wrong by using just m. The answer is option A. Follow at Superschool IIT JEE for daily JEE solutions.